So here's a wild thought. What if the laws of physics aren't permanent? I know, it sounds like something out of science fiction, but it's a very real question that physicists are asking. We're going to dive into this radical idea that the fundamental rules of our universe might not be so fundamental after all. I mean, really think about that for a second. The speed of light, the force of gravity, the charge on an electron, we call them fundamental constants for a reason, right? We assume they've always been the same and always will be, but what if they haven't been? What if the very fabric of reality has changed over cosmic time? So you've got two basic camps here. On one side, you've got the standard view, which has been the bedrock of science for centuries. The laws are constant, period. It's the simplest explanation, and as Occam's razor tells us, you shouldn't make things more complicated than they need to be. But then on the other side, you've got this radical idea. What if the laws are dynamic? What if they evolved, maybe cooling down and settling into the stable state we see today? Okay, before we get too carried away with that, let's bring it back to Earth for a second. Let's look at the actual evidence. Why do pretty much all physicists believe the laws are constant? Well, it really comes down to what we can see with our own eyes, or, our giant telescopes. When we look at a galaxy that's, say, 10 billion light years away, we're not just looking across space. We're looking 10 billion years back in time. And what do we see? We see stars forming, gravity pulling things together, all following the exact same rules we see today. The light from those ancient atoms acts like a fingerprint, and it tells us the rules of quantum mechanics and electromagnetism were the same back then as they are now. That is some seriously strong evidence for consistency. And I love this quote because it just perfectly captures how scientists actually think. They aren't rigid. If we found solid proof that the speed of light, what we call c, was a little different in the Andromeda galaxy, we wouldn't just throw up our hands. The model would change. Our law for the speed of light would get a little asterisk that says, except over there, for some reason we don't understand yet. And then, of course, the big new mission would be to figure out that reason. But until you find that evidence, the simplest, most powerful assumption is that the laws are the same everywhere. So the case for consistency is really strong. But, and there is a but, there are a few places, some really extreme environments, where our current rulebook just completely falls apart. These are the two great big mysteries. Deep inside a black hole, Einstein's theory of general relativity predicts a point of infinite density, a singularity. That's not a real thing. That's the math screaming at us that the theory is broken. And we see the exact same problem if we try to rewind the universe all the way back to the Big Bang. In that very first instant, our physics models just stop. They can't describe what's happening. So how does scientists deal with that? Well, the standard response isn't to say, oh, I guess the laws of physics were just totally different back then. No, the assumption is that our models are what's incomplete. We're missing a piece of the puzzle, some deeper theory, probably a theory of quantum gravity, that can explain these extreme situations without breaking. But what if that missing piece is something far, far stranger than we've imagined? This is where we get into a truly mind-bending hypothesis that actually takes this idea of evolving laws seriously. It's called cosmological natural selection. It was proposed by the physicist Lee Smolin. And yeah, it is exactly what it sounds like. It's taking Darwin's brilliant idea of natural selection and applying it not to living things, but to entire universes. So how on earth would this even work? Well, the idea goes something like this. Step 1, a black hole forms in a parent universe. Step 2, when that black hole collapses, it doesn't just hit a dead end. It actually bounces and creates a brand new child universe. Step 3, this new universe gets most of its physical laws from its parent, but with tiny, random mutations to its fundamental constants. And step 4, this is the key, is selection. Universes whose laws happen to be good at making lots of black holes will naturally have more children. They are more fit in a cosmic sense. And the result of all this? The outcome is pretty profound. It would mean that over countless generations of universes, we'd end up in a multiverse where the most common type of universe is one whose laws are perfectly optimized for making black holes, because those are the ones that reproduce the most. Our universe's laws wouldn't be random at all. They'd be the result of eons of cosmic evolution. Now, this might just sound like a really cool science fiction story, but here's the thing. It actually offers a potential answer to one of the biggest, most stubborn puzzles in all of physics. And that's the famous fine-tuning problem. It's a simple question. Why do the laws of our universe seem so ridiculously, perfectly balanced for complexity, for stars, for galaxies, and ultimately for life like us? Physicists call this fine-tuning. It's this bizarre observation that if you imagine the universe has a control panel with knobs for all the fundamental constants, you find that those knobs are set to incredibly precise values. If you were to just nudge one of them, even a tiny bit, the whole universe could become sterile and dead. Here's a classic example. You've got the strong nuclear force that glues protons together inside an atom's nucleus, fighting against the electromagnetic force that's trying to push them apart. If you made the strong force just a tiny bit weaker, electromagnetism would win. Protons would fly apart, no atomic nuclei could ever form, which means no atoms, no chemistry, no stars, no planets, no us. The whole cosmic experiment would be a bust. And the scale of this problem is it's mind-boggling. String theory, which is one of our best shots at a deeper theory of physics, suggests that there isn't just one way for the laws of physics to be. It suggests a landscape of possibilities, maybe as many as 10 to the 500 different possible universes, each with its own set of rules. That's a one with 500 zeros after it. So, out of all those possibilities, how did we get so lucky to land in one of the very few that actually works? Well, putting aside any supernatural explanations, you're left with two main ideas. The first is called the anthropic principle. It basically says, look, if there are 10 to the 50 universes out there, of course we find ourselves in one that can support life. We couldn't be having this conversation in one of the dead ones. The second idea is cosmological evolution. It's not random luck at all. Our universe's constants are the direct result of a cosmic survival of the fittest. Ultimately, this whole debate, whether the laws are constant, whether they evolve, why they're so fine-tuned, it all feeds into the grandest ambition in all of physics. And that is the search for a theory of everything. It's the holy grail, a single, elegant framework, maybe even a single equation that can explain every physical interaction in the universe and unite all four fundamental forces of nature into one beautiful picture. And if you look at the history of physics, it's really a story of unification. It started with Newton, who realized the force pulling an apple to the ground is the same force keeping the planets in orbit. Then Maxwell came along and unified electricity and magnetism. In the 20th century, physicists unified that with the weak and strong nuclear forces, giving us what we called the Standard Model. And now there's just one final step, bringing gravity into the family. So that's why these wild ideas like evolving laws are so much more than just philosophical games. They are serious, creative attempts to find a new way forward. They're part of the search for that deeper reality that can finally solve the massive incompatibility between our two best theories of the universe: general relativity for the big things and quantum mechanics for the small things. And that leaves us with this one final, really profound question. If the laws of physics can evolve, it completely changes how we see our place in the cosmos. It suggests that our universe, with its perfect life-giving balance, might not be a miracle or some cosmic jackpot. It might just be one successful branch on an immense cosmic tree, one thriving experiment in a multiverse of countless failed attempts. And that is a pretty staggering thought.